Hi class. So let me talk about one way to fix this. Now the way that people often think about when I introduce this problem is they start thinking about how do I model this system, okay? And this is exactly the first way that I'll explain this. We can model the maximum change, right? Our speed, we can model acceleration, we can model deceleration. Okay, we can do all of this basically using simple calculus and physics. Okay, basics, high school level physics. It's not hard. And the way that it works is like this. We can model max change using the model of how you expect it to work. So we can use, in addition to having t, right, we have t speed. And what this does, if we have this variable called t speed, we can go, here's how quickly t is changing. Rate of change of t. Now, if we just use t speed, and each frame we add t speed to our t, we now have the exact same thing as our straight line. It's going to move up the same increment each time. We have a linear result. But here's where things get interesting. In addition to t speed, I can model a t acceleration, okay? Which tells us how much does the speed change every time. Rate of change of t speed, okay? So, and then if we have this, it actually becomes really simple to implement. We use it like as follows. Where am I? Yeah, there we go. First we go t speed plus equals t accel each frame. I should probably say that. So each frame. The first thing we do is we modify the speed. We add our acceleration to the speed. So it's accelerating. It's getting faster, okay? And then once we have our speed, then we just modify our t, right? T plus equals t speed. So with this model, we go, okay, this is how much I want t to accelerate. How many pixels per unit squared, say, if you know your acceleration. Per second squared, I should say. And then you can use that acceleration to modify the speed, use the speed to modify the time, and we have a really simple model. And the nice thing about this model is that it gives us the full control over the acceleration and, it's an and, deceleration, okay? So we get full control, and this is actually quite nice if you have like an open-ended model and you don't know what the end point is, you don't know where you're going. Think a character in a video game, think a car, think a vehicle. You can just, I don't know where I'm going to go, but I know that I want to accelerate and I have a maximum speed, I have a current speed. You can model this quite simply. I'll give a demo in a minute. But very quickly with our problem here, we start seeing some holes in this approach. So we have some questions. First of all right, I can accelerate quite easy. I start at 0, my speed is 0, cool. I add my acceleration, I slowly speed up. So if I've modeled this acceleration, but then how do we decelerate? Okay, when do I start deceleration? When do we start deceleration? Right? So if I'm going to draw this graph again, this is my t 0 to 1, this is my time. So far, my approach of just using acceleration is quite nice. It'll accelerate nicely, but it's going to keep accelerating, right? So our first thing is, I should also write that down. Do we have a maximum speed? Right, so the first thing I need to do is implement a maximum speed, right? The other question is, if I want to decelerate, when do I start decelerating? Okay, so that I hit my t of 1 at the right spot. Do I start decelerating halfway through at t of 0.05? If I start decelerating too early, I'll stop before the end. Wait a second, now I need to model that. Okay, so if we're going to use this kind of approach where we model the speed and acceleration and we modify those variables, it's kind of like the animation we talked about earlier. If you manage everything locally, you get all this control. But if you want global solutions, like I want to decelerate and stop right on that spot, right at that keyframe, it gets quite tricky. Quite tricky to get right. So I'm going to give a demo and we'll go through it. But basically, let's use this for open-ended problems. Let's use it when I have a vehicle I want to move. I'm not trying to get to an endpoint. And then maybe not for closed problems. For example, the keyframes. And I'm going to show a demo of this, but as you'll see in my code, it's a bit clunky. It'll work really nicely if I have it open like a video game character I'm trying to drive around. It doesn't work nice for trying to interpolate between keyframes. So let's switch over to desktop slides, and I don't know why it crashed. So here's this lerp acceleration program I created. And what's happening here is the same keyframes as always. There's nothing fancy here. What I've done though is in addition to having instead of having a current keyframe that not a keyframe rather, a current frame, an in-between number that we keep track of, and then calculate a t from that. I keep track of my t globally, set it at 0. I have a t speed, it's at 0, and an acceleration rate. This is acceleration of how much the speed changes each frame, or how much the motion will change every frame squared, right? And then I have a maximum speed and all these kinds of things. I've also set up an acceleration region, so it'll start decelerating 3/4 of the way in, okay? And the way that we implement this is quite simple. In my draw function, I have my keyframes, just like before. And then I check, is t past my deceleration range? If it is, I reduce the speed of t. Otherwise, I increase the speed of t. And then I calculate my speed, make sure it doesn't go above my maximum speed and go below 0. Negative speed doesn't make any sense. I guess you're going in reverse. And then I add my speed to my t. So this might take a bit to get your head around, but each frame, what speed am I going? Add that to my t. I should move along that same speed every time. But I'm also modifying the speed. I'm accelerating or decelerating. So what I've done now is I'm still using lerp. I'm still using a linear interpolation that's using my t to go between two values, current and next. Okay, I'm still using a linear interpolation, but the difference is t is not changing linearly with time. I'm modifying t in a very nonlinear fashion. So let's see what this looks like. So see, nice, accelerate in, accelerate in, and then it's a bit clunky to stop. Seems to stop quite suddenly. There we go, that one looked pretty nice. Go fast, and then it slowed down a bit. Huh, where am I? So we can change the region that it decelerates at, and we can modify this. So instead of starting to decelerate at 0.75, let's change it to 6.5 and see what happens here. Oops, there's my code. So you see it speeds up and starts to slow down right earlier. There we go. Speed up and then slows down a little earlier, but didn't quite slow down fast enough. So you can see that we're now starting to get into the realm of twiddling our parameters to get the effect that we want. In this case, because we're doing keyframes and we want to go between them smoothly, this is the wrong tool for the job. It's nice to think about, and I like to show this because this is how people often, like if I ask a class, how will I do it? They say, let's do it this way. Cool, great. But it's tricky because it's you have to solve it. It's an open-ended approach when you're trying to solve this closed system where I have endpoints. We could do it algebraically, but it gets messy. It's not typically how we want to think about it. And as you might have guessed already, there's a better way, and I'm going to show you. This better way. All right, so let's come back and let's learn about a different way to approach this problem of nonlinear interpolation.